Assalamu alaikum. Let's discuss another example. Let's assume we have the following block diagram. The input is R of t, comparator. This signal is E of t. Now E of t will go through an analog to digital converter with sampling frequency f equal 10 Hertz. So this will be E of k. Now let's assume we have a digital filter or digital controller which is D of z. So this will be U of k. Now let's assume we are using a digital to analog converter. So this will be the U dash of t. And here we have a plant, the process, a GP of S, and the output is Y of t. And let's assume this is a unity feedback control system. Now this one is the discrete platform. The other signal is continuous. So here we have a discrete. Now let's assume that the controller, the digital filter, and the plant is given in terms of the discrete equation and differential equation. So let's assume the following equation represent the digital controller and the continuous time plant. Respectively. So the digital control is given by U of k is equal to U of k minus 1 plus 2 E of k minus 1. And the plant is given by a differential equation, first order, let's assume dy by dt is equal to minus 5 y of t plus 4. The input is u bar of t. So sometime I will use dy by dt, or sometime you can represent this one as y dot. Each dot represents a first derivative. So at first we need to find d of z, the digital controller. Now this difference equation in z domain can be read as u of z will equal to z minus 1 u of z plus 2 z minus 1 e of z. Now from the block diagram, d of z represents the relation between u and e. So the output is u of z and the input is e of z. So if we spread the variable, we can get 1 minus z minus 1 u of z will equal 2 z minus 1 E of Z. So from here, U over E can be written as 2Z minus 1 over 1 minus Z minus 1, which can be written as 2 over Z minus 1. Now, let's assume we need to find GP of S. Now, we stated that the plant, this is the plant, is represented by ordinary differential equation. So simply, in S domain, and I'm assuming that the initial condition is equal to 0. So this will be S y of S will equal to minus 5 y of S plus 4 u bar of S. So simply y of S over u bar of S will equal to 4 over S plus 5. So now we find d of z and we find GP of z. Now let's assume that the whole device is used as a zero order hold. So let's assume that the whole device is a zero order hold. You know that the whole device can be a first order hold also, but the most common one is the zero order hold. So we need to find the closed loop pulse transfer function. So if the used hold device is a zero order hold, we need to find the closed loop pulse transfer function, which is y of z over r of z. Now if we replot the block diagram, this is r of t. Here we have a comparator. Here we are representing the analog to digital converter by a sampler with a sampling t equal 1 over 10, which is 0.1 second. Now this is the d of z, and here we are representing the zero order hold with the plant as g of s. So this is actually 1 minus exponential minus t s over s, which is the transfer function of the zero order hold, multiplied by gb of s, which was 4 over s plus 5. And here we have y of t, let's say, and this is a negative unity feedback. So simply this can be written as r of s, this is e of s, this is the e star of s, and this is the y of s. So first let's find the closed loop pulse transfer function in terms of the dg. So the first thing I will write the output, which is y of s in terms of the inputs. Now here we have input, output. Now the real input is r of s, and the real output is y of s. Also, if we have a sampler, we will consider the input to the sampler as output, which is e of s, and the output of the sampler as input, which is the e start of s. Then we try to write the output in terms of the inputs. So y of s will equal, you know that if we have d of z, this means that we have d star of s, because d of z and d star of s is related by z equal exponential of ts. So y of s will equal d star of s, g of s, e star of s. If we take the start for the both equation, so we have y star of s is equal d star of s, g star of s, e star of s. So this is the first output, which is the real output. So this is the real output. We call it real output and real input. Now let's write the artificial output, this one, e of s in terms of the input. So e of s will equal r of s minus y of s. If we start both sides, so e start here, r start here, y start here. So now we can substitute this one here. If we do so, then we have the y start of s is equal d start of s, g start of s multiplied by r start of s minus d start of s, g start of s multiplied by y start of s. If we spread the variable and solve, we can reach to y start of s over r start of s is equal to d start of s, g start of s over 1 plus d start of s, g start of s. So this means that we know that if we need to find y of z from y start of s, then simply this means that we need to use the relation that z is equal exponential of t s, or simply s is equal 1 over t ln z, which means that if we have the start function, we have the function in terms of z. So now we can write y of z over r of z, which will equal d of z, g of z over 1 plus d of g of z, d of g, g of z. Now we have this one. We need to calculate g of z. Now we recall that g of s is actually the zero order hold 1 minus exponential minus t s over s multiplied by gp of s, which was 4 over s plus 5. So if we need to calculate g of z, we need to find the z transform for g of s, which will equal to z minus 1 over z, the z transform for the gp of s over s. So this will read as z minus 1 over z, the z transform of 4 over s plus 5. So now let's find the z transform of the 4 over s multiplied by s plus 5 using the residual method. So here the poles are, we have s equal to 0 and s equal to minus 5, so we have simple poles. Recall x of z will equal the summation of the residue of x of s z over z minus exponential t s at the poles of x of s. Now here we have a symbol poles at s equal to 0 and s equal to minus 5. So R1 will equal the limit when s go to 0, s multiplied by x of s, which is 4 over s plus 5 multiplied by z over z minus exponential of t s. And if we evaluate at s equal to 0, this will equal 4 over 5 z over z minus 1. Now the second residue R2, which is at s equal to minus 5, so this will be the limit when s go to minus 5, s plus 5 multiplied by the function itself, 4 over s plus 5 z over z minus exponential of ts. Now if we evaluate, this will equal minus 4 over 5 z over z minus exponential minus 5t. So now we need to calculate this one. So this one will equal R1 plus R2. So R1 plus R2 will equal 4 over 5 z over z minus 1 multiplied by 1 minus exponential minus 5t over z minus exponential of minus 5t. Now we need to find g of z, which will equal to 4 over 5 z minus 1 over z multiplied by R1 plus R2 z over z minus 1, 1 minus exponential minus 5t over z minus exponential minus 5t. Now remember, t will equal 1 over f, which will equal 1 over 10 hertz, so this will equal 0.1 second. So let's simplify. This will give us g of z will equal to 0.8, 1 minus exponential minus 0.5 over z minus exponential minus 0.5, which will equal, if we evaluate, 0.3148 over z minus 0.6065. So now we need to find the closed loop pulse transfer function, which is y over r, which equal to it was dg over 1 plus dg. Now d of z was equal to 2 over z plus 1. G we already calculated here, which is 0.3148 over z minus 0.6065 over 1 plus 2 over z plus 1, 0.3148 over z minus 0.6065. Now if we simplify, this will equal to 0.6368 over z minus 1. Sorry, this one is minus 1, minus 1. Let's see it. Yeah, 2 over z minus 1. Sorry for that. So this will be z minus 1 multiplied by z minus 0.6065 plus 0.6368. Finally, y over r is equal to 0.6368 over z square minus 1.6065 z plus 1.2433. Thank you.